One of the really cool uses of mathematics and mathematical thinking is that it allows us to take a look into the future and try to predict what we might see. This is the amazing world of probability, where we're going to try to give a numeric value to the likelihood of something happening or not happening. Now, computing probabilities, isn't that really too painful? In fact, it's pretty easy when the likelihood of any particular event is actually going to be the same. So here's the notation. We write P of event to mean the probability that a particular event occurs, and that equals this ratio, the number of favorable outcomes that would actually lead to that event, divided by the total number of outcomes in the sample space, where we're assuming that each possible outcome is as equally likely as any other. So let's take a look at an example where you can actually see this idea happening live. So, in the first one, we're told that we have 6 hardback books and 11 paperback books on a shelf. We're just going to reach down and grab a book without looking. So we're not going to be looking at it. We're just going to go, and they're all mixed up. So the question is, what is the probability that we randomly pick a paperback book without looking? Well, let's take a look and see how we can actually apply this formula to produce the probability. So we write this as the probability paperback, meaning the probability of picking a paperback book. Well, let's see. We take the number of favorable outcomes. Well, how many paperback books are there that we could possibly pick? Well, there are 11. So we see 11. And I divide that by the total number of outcomes. Well, what are the total number of possible books I could pick out? Well, I could pick out a hardcover. I could pick out a paperback. So the total is the sum, which is 17. So the probability of picking a paperback book is going to be 11 over 17. Now, it's interesting to notice, if you look at this formula or the answer, that we can see that the probability of an event, this particular fraction, will always be a number between 0 and 1. Now, we could write it as a percent, but if we write it as a decimal or a fraction, we'll see the number is always between 0 and 1. The closer that number is to 1, the more likely the event is to actually happen. The closer the number is to 0, the less likely it is, the more likely it is that it's not going to happen. 11 over 17 is actually fairly close to 1, so we would expect that it's actually more likely than not that we might actually pick out a paperback book. When you look at the numbers, it makes sense, because it looks like there's almost twice as many paperback books as hardcover books, so it would seem clear that it's probably likely that we're going to pick out a paperback book, and here is the actual numeric probability, the quantification of that observation. Neat. All right, let's take a look at another example together and see if we can put this formula to good use. So in the next example, we're told that we have 2 number cubes that are rolled. So we have 2 number cubes. I actually want them to look different so we can distinguish them from each other. And I'm going to roll them. Here I go. I'm going to roll it live. Let's see what we get. I see a 6 and a 3, and that produces a 9. Well, in fact, this is very interesting, because take a look at the question. So the question is, if all the numbers are equally likely, what is the probability that the sum is 9? All right, well, we can actually figure this out by making a list out of all the equally likely scenarios. How do we do that? Well, I take a look at all the possible scenarios for the different possibilities for the fuzzy number cube, and then I look at all the possible ways that the red number cube can land, and I make a grid together. A grid with all that information. That grid would be pretty big, because there's 6 possibilities for the fuzzy number cube. There's also 6 possibilities for the red number cube. So in total, there's 6 times 6. And we see, in fact, 36. So what we see is this chart here. So these are the first numbers represents what we see on the fuzzy number cube. The second numbers you see here, like this 2, is for the red. So the one I actually rolled, which was 3, 6, would be 3, 6. It's right there. So we're trying to find the probability that the sum is 9. Well, take a look at all these equally likely possibilities and see where do the sum of these 2 numbers equal 9. Well, these are all very small here. This is 4, this is 5, this is 6, this is 6 as well. This is 7. But wait, way over here, the one that we saw, that's what I got. That's 9. In fact, 4 and 5 make 9. 5 and 4 make 9. and 6 and 3 make 9. So all those scenarios, in fact, would lead to 9s, and all the other ones would not. These would be bigger than 9. These would be less than 9. And so, what do we see? Well, the probability that the sum is a 9 is going to equal exactly, well, the total number of successes, which is 1, 2, 3, 4, divided by the total possible outcomes, which we've already seen as 6 times 6, or 36. And so when we simplify this, we see 1/9. Well, 1/9 is actually a very small number. So in fact, if you were to roll 2 number cubes, you would not necessarily expect to see the sum is going to equal 9, because in fact we see the probability is somewhat low. And yet, of course, we think that every once in a while we should be lucky and hit it, just like I hit it right there out of the get-go. Pretty cool. Anyway, the important thing is we can find probabilities, we can associate a number to how likely something is to have happened or not.